Alright, another fun day in CCNA1. Hope you enjoyed Chapter 6 and the Chapter 6 packet tracer. Now we're moving on to Chapter 7, which is very, very complex. Yeah, that's the best way to explain it. Describe the purpose of the transport layer in managing the transportation of data in end-to-end communication. Describe characteristics of TCP, the TCP and UDP protocols, including port numbers and their uses. Explain how TCP session establishment and termination processes facilitate reliable communication. Explain how TCP protocol data units are transmitted in knowledge to guarantee delivery. Describe the UDP client process to establish communication with the server. Determine whether high reliability TCP transmissions or non-guaranteed UDP transmissions are best suited for common applications. Alright, so the role of the TCP layer. Well, this is where we can start to get sometimes reliable connections and connection-oriented connections. Remember, that's where we establish an actual link. And so what are they saying here? The transport layer moves data between applications on devices in the network. Alright, so last step before we hit the application layer, transport layer. It has both TCP and UDP, and we'll find out what they're for. Alright, so transport layer, it tracks individual conversations, segments data and reassembles segments, identifies applications, right? So it's part of the reason we can do multiple things on a computer instead of just one task at a time, right? We can segment into different applications as it's showing there. We can segment network traffic so it goes to those right applications, and we can identify what application by port numbers. So conversation multiplexing, and maybe you guys remember multiplexing from when we were talking about it in the physical layer, but this multiplexing, it's just segmenting out by applications or chunk of time, somehow identifying traffic on one line to be split up and used for different services. Right? So what does it say here? Segmentation allows conversation multiplexing. Multiple applications can use the network at the same time. Segmentation facilitates data transport by the lower network layers. Error checking can be performed on data in the segment to check if the segment was changed during transmission. Transport layer reliability. Okay, so we have two different types of reliability, and it depends on the application we want. So if we have a high moving application or something we don't really care about, we use UDP, right? So it's showing us TCP can be DNS, UDP can be DNS, UDP can be TFTP. It's usually voice and fast applications, gaming applications, and the rest of it's like reliable stuff, such as email and HTTP and file transfer protocols. So if we want to guarantee it gets there, we're going to use TCP. If we're just going to send it down the line, we're going to use UDP, and we're going to see that, but I don't know. SMTP is more than just email. You guys are going to need to start learning port numbers and these protocols, what they do, right? HTTP is our web access. FTP is how we download files. SMTP actually is what sends our emails. Then we have POP and IMAP to receive our emails on the server and load into our application. TFTP is how we usually flash BIOS, or we can do network configurations. And DNS is domain name services, right? And so that's what allows us to type in netacad.com and go to the right IP address, or google.com, instead of having to type in 8.8.8 or something like that. So, but our two major, what you need to take off of this slide is our two major transport protocols are TCP and UDP. There are other ones, but these are our two major ones. So first, TCP. So what's good about TCP is it actually tracks our data segments and acknowledges data being sent and retransmits anything that was sent that wasn't received. So if we want to make sure something gets there, we use TCP, right? So as you can see, it's sent there, and the server will then send back and acknowledge it. But because of these acknowledgments, or the resending of them from not being acknowledged, TCP is much slower than UDP. So we can't use it for, say, VoIP or technologies that need speed. So then we have UDP, which is not reliable. It doesn't care if it gets there. We just send it, right? We send it, either gets there or it doesn't. If it gets out of order, UDP doesn't. TCP will show the order that the segment should be reassembled in. For UDP to do that, it actually has to happen at the application layer. So a programmer would have to program their, say what they just showed there, their TFTP server to reassemble the data in the correct order. If they did not, it would just have to be resent. And so, as we've been kind of saying, our slower protocols that we want to make sure we get, TCP, or maybe it doesn't need speed, TCP and web, or TCP is web and POP and email, those kind of things. Right? It's reliable, acknowledges data, resends lost data, delivers data in the sent order. That's TCP. Then our UDP, right? We have phones and video streaming. Fast, low overhead, does not require acknowledgments, does not resend lost data, delivers data as it arrives. Okay, so what are we trying to get to here? So this has to do with both, right? Basically, I think they're trying to tell you that there's port numbers for both TCP and UDP, and they do different things. They're primary, like either one, anything in the transport layer, it's tracking the individual communications between applications on the source and destination host, right? So our port numbers actually tell us what application we're using. And then another primary task of either of these is segmenting data for manageability and reassembling the segmented data into streams of application data at the destination, and to identify the proper application for the stream. I thought we already talked about this. Oh, I must have clicked back. All right. So introducing TCP. Alright, so TCP is probably the harder one to understand out of the two. And so it stands for, as you can see, Transmission Control Protocol. And so it's connection oriented. Remember, and connection oriented means that it makes sure, right, if we're sending from, actually it needs to be a computer. So if we're sending from computer to computer, and that could be across a big network, but they're just connected, right? So if we're sending from this one to this one, remember IP was not connection oriented, it just sent it. And so now TCP is. So what it does is it actually does a handshake to make sure that this guy is on before it sends. And it's a three-way handshake, but we're not quite there yet, but that's what it does. So connection oriented, reliable delivery, right? Because it checks to make sure the person receiving it sends back ordered data reconstruction, it has segment numbers and all that, and then it has flow control, which has to do with, maybe remember, speed, like Windows, how fast we're sending it and how slow we're sending it. Probably I would say window size. So establishing a session, TCP is a protocol. It's connection oriented and negotiates and establishes a permanent connection or session between source and destination. That's all you need to know there. Reliable delivery, TCP can implement a method to ensure reliable delivery of data. That's all you need to know there. same order delivery. Because networks may provide multiple routes that can have different transmission rates, data can arrive in the wrong order. TCP reassembles at flow control. Network hosts have limited resources such as memory bandwidth. When TCP is aware that these resources are overtaxed, it can request that sending an application reduce the data flow that is done by the TCP, regulating the amount of data the source transmit. Flow control can prevent the loss of segments on networks and avoid the need for retransmission. So what it's saying is if we start messing up, we're going to try to lower our window. We're constantly adjusting the size, how much we send, right? We want to send as much as possible in one, but not if we have to resend it. So if it starts erroring, we get smaller and smaller. If we're doing great, we get bigger and bigger. And so that's what's happening. The role of TCP. Alright, so this is the TCP segment, right? And so, right, we're going to have a UDP UDP header and a TCP header. And so remember, all that's going to have the application layer data inside of it. But here's what we have. We have sequence number, right? Used for data reassembly. We have acknowledgement number. Indicates the data that has been received. Known header length. Alright, you know, same length that we've been seeing. This field reserved. It's reserved for future use. Who knows when. Control bits includes codes or flags that can indicate the purpose of the TCP segment. Window size indicates the number of segments that can be accepted at one time. So that's the size as we're sending it. And then checksum, used for error checking. Urgent indicates if the data is urgent. Okay. So we have quite a few there, and I don't know why, but the most important two things or actually probably the most important is usually, well, it's either source or destination depending if you're a client or a server, but we'll get to that in a second. So don't forget that the source ports are up there. Now UDP, connection list, just like IP, right? It just sends it. If it gets there, it gets there. So it's unreliable. It's best effort protocol. No order data reconstruction, but that is not necessarily true. It's just handled by the upper layer. If we look here, the data is simply delivered to the application in the order it arrives. But somebody could program in to their application to reorder it in the correct order. But it would have to happen at the application layer. No flow control. Alright, it just sends it. It doesn't try to adjust it because it's not checking, right? TCP, what's adjusting our window size is that we aren't getting acknowledgments and we're having to resend. So we're going to shrink our window size until we get the perfect one and then try to make it go bigger, and constantly doing that so we can have the most data. UDP doesn't care. It's not checking to see if it got there, so it cannot adjust window size. The role of UDP, well, we've already talked about it, right? It's VoIP. And so, as you can see, if we look at the role of UDP versus our segment, right, our UDP segment is about half the size, right? It's really simple. It has the length of it, it has the source port, the destination port, and an error checksum, and then the application layer. That's it. That is all it has. It's really easy. So here's some of our port numbers that we need to know, right? So we have an HTML page running on port 80, probably important to know. Mail running on 110, and so that 110 port, what that is POP3, which is Post Office Protocol. So that's one way to receive email, and I am not really sure what 531 is. Some kind of messenger service. Does it tell us here? Anyway, so how we are identifying applications is through this port number. And so that's how the computer, right, we have one wire in this computer. How does it know what data is going to what application? Well, our transport layer has a port number that says, oh hey, this is where you're going. And actually all of these wouldn't be coming into the computer. These would be going to the server that they were on, and we'll find out what the computer actually does. So the destination port from the computer is the actual application of the website, right? So we send this to Google. What it uses, the source port is then randomly generated by sending the device to identify a conversation between two devices. This allows multiple conversations, right? So it's just randomly generated. If we use port 80 coming in, we could only go to one web page, right? Or, well, we technically could go to more, but that's just what they're saying right here. And we'll find out where the randomly generated port number is, because we have ports that we have well-known port numbers and other port numbers that's coming up. So anyways, this computer sends to the server and it says, hey, destination 80, the server knows it needs web traffic. It has a source port of 1085, and so on the way back, this was the way there, and so then on the way back, the server has a destination of 1085, which was this number right here, right? The destination becomes the source on the way back, and the source being the destination. Okay. And that's what they're showing here. Right, well actually this is both from the computer to the server, and if we saw it coming back, it would be inversed, as I said before. So when we have an IP address, this is important. The combination of source and destination IP addresses and source and destination port numbers is known as a socket. The socket is used to identify the server and service being requested by the client. So that's a terminology you should remember. Socket, S-O-C-K-E-T. Okay, so now here are port numbers. So these random generated ones are supposed to be these high number, well actually they're supposed to be registered, but I have seen them actually go with dynamic private ports, and that's probably why that last port said it's just a randomly generated. But the well-known are the good applications, right? So the well-known ports, these are reserved for services and applications. They are commonly used for applications such as HTTP, Internet Message Access Protocol, IMAP, which is email, Simple Mail Transfer Protocol, which is sending email, and Telnet. By defining these well-known ports for server applications, client applications can be programmed to request connection for that specific port and its associated service. Alright, registered ports. These ports are assigned to a user, processes, or applications. These are primarily individual applications that a user has chosen to install rather than common applications that would receive a well-known port number. When not used for a server resource, these ports may be dynamically selected by the client as its source port, also known as ephemeral ports. These are usually assigned dynamically to client applications when the client initiates a connection to a service. The dynamic port is most often used to identify client application during communications, whereas client uses the well-known port to identify and connect to the service being requested. On the server, it is uncommon for the client to connect to the server using a dynamic or private. Although, as it says down here, your illegal peer-to-peer programs usually do use these super fishy ports. So, want to block peer-to-peer, block these ones, but it could cause some problems from your users doing legal applications. Make sure you go through and look through some of these port numbers. Probably these well-known port numbers right here you should know. IRC you don't need to know, but 443, 143, 80, 25, 23, 21. Make sure you know SSH. I believe that's 22. So yeah, you need to know all of those ports. Well-known UDP ports. There's more than just TFTP, but anyways, Go ahead and look through there. There's some good information. Maybe Teresa has you guys studying port numbers already. Maybe not. Or maybe not. Actually, I guess that'd be A+. So maybe you're studying port numbers in A+ and security. I don't know. Okay, so NetStat. NetStat is going to show us the actual TCP connection, right? Our local address. It's and what port we're going to. The colon shows what port we're going to, right, and where we're going. And so this is all the established connections, right? Source port, where it's going, destination port, and connection state. So that's NetStat. Great server tool. NETSTAT, NetStat. Enter. Alright. So, TCP and UDP, what are we doing next here? Segmentation. So, how they handle segmentation, right? So, all this is saying, if you click, is that UDP, has a simple source and destination port, whereas TCP has all the other stuff that's included in the TCP header, right? So source and destination, sequencing, acknowledgements, and flow control information. So that's the difference in segmentation on these two. And so which one is going to take more resources? Well, hopefully you figured out it's TCP. Alright, what are we talking about here? The key distinction. How is TCP reliable? So when we send there, well, kind of been really talking about this, but one of the ways is, right, it establishes a connection. And then it sends the data and, monitors for flow control and all that, and then at the end it says goodbye, right? So it actually disconnects between the two connections when it's done. So server TCP processes. Let's see if it's given us our four-way handshake or if it's just given us more port numbers. Alright, so this is just the inverse of what we've been talking about the entire time, where these guys are going to send for the application they want, and then the server is going to inverse and send back to them. Make sure you understand that. So now here's a more important part, how we establish connections, right? So the first thing we do is send a SYN. Alright, so this is sending to a server. So since this is establishing the connection, this is how we form connection-oriented process. So first, SYN. So the server receives SYN, and it sends back SYN ACK, right? So the SYN ACK is received, and so then we receive and acknowledge that we have to the server that we have established a connection. Alright, so that's a three-way handshake. Make sure you write this down because it is a three-way handshake, which is SYN, SYN ACK, and ACK, right? Those are our that's our three-way handshake. Sending the SYN, the server sending back the SYN ACK, and then the client sending an acknowledge that we have formed a connection. So after we formed that connection, we next send all of our data through, and then we're going to shut it down. So what they're showing here is just more Wireshark. You can use Wireshark in the same way. Go to a website, you can see a TCP one, maybe do some TFTP, or I don't know, use Skype, see if Skype is UDP, I think it is, and you could look at both the difference between TCP and UDP. We may do a lab in class about this if you guys want to. Let me know. But this three-way handshake would be good stuff to know. So look at that. So then we look at the termination. So remember, we had a three-way handshake, right? SYN, SYN-ACK, and ACK. So now, what do we do after the end? FIN-ACK, or FIN-ACK, FIN from the other side, and then an ACK from the other side, right? So we have FIN, it's received by the computer, so it says ACK. So then, same station, this is where it's different than the other one, it says FIN, and then our client says ACK, and our connection is ended. Okay, so that's the termination of the connection. And so it's a four-way termination. Four-way handshake termination. Alright, so flow control is where this gets very complicated. Okay? So you're going to want to read all, but so we have just the basics. Alright, so because we're using IP, we can take different routes, right? So it's load balanced over this network, so it arrives wrong, or in different order than it was planned. So these segment numbers are the first part of the flow control. We put them back together in the right order using segment numbers. Alright, so now beyond the segment numbers, we need to look at window size, acknowledgments, and window size, because this is where the amount of data that we're sending is through the TCP connection comes in. And so how it does that is our window size is the amount of segments we can receive. So if we're doing great, we can receive a whole bunch of segments, but as it gets worse, we shrink it down. So how do we figure that out? On the segment size, or the sequence size, we have a sequence number. Okay, so it is sent, right? So the sequence number and acknowledgement number are used together to confirm the receipt of the bytes of data. Okay, so then what the acknowledgement is we send some sequence. The acknowledgement sends back, when it receives the window size, the acknowledgement of what it expects to receive back. So if we look at our demonstration down here, we don't have to worry about the port numbers here. We're worried about, okay, so this guy's sending 10 bytes, and he's sending the first byte. It has a sequence number of 1. So then it's sending back 1 byte with an acknowledgement number of 11, right? Because it's received 10 bytes, so now we're on 11, and so now the other side sends 11. If there was an error, like if it sent back 1 on the acknowledgement, it would resend this first one, and that's where we get a lot of lag from TCP. Okay? And there's a little more to that, and that's what we're going to see in this loss. But, well, maybe I'll go over this real quick. So TCP uses the ACK number sent back to the source to indicate the next byte the receiver expects to receive. Alright, so that's called expectational acknowledgement. But the acknowledgement's all based on when it's going to send the acknowledgement is all based on window size, as we will find out here. So networks get busy, and so something is going to send wrong. So we send segment 1, timer runs, acknowledgement 1 sends, it says it expects to receive segment 2. So segment 2 is sent, segment 2 was not received, so it doesn't send acknowledgement 2. Timer times out, and so what's it going to do? It's going to resend segment 2. Now what if there was a bunch of data running, right? The acknowledgement request for 3, well, our acknowledgement would be wrong, right? If it received a whole bunch of data, like say it resent 3, and then 3 wasn't received, and it sent back an acknowledgement for 2. That's how TCP works. Alright, so to window size. This is what I've been talking about. So our sequence number 1 is 1500 bytes. Our window size is 3000, so it sends 1500 bytes. Then it sends 1500 bytes again, 1501, right? So what's it received now? It's received 3000. So our acknowledgement is going to be 3001. Why is it sent at 3001 and not up here? Our window size is 3000. So as soon as it receives 3000 bytes, it's going to send back an acknowledgement. And then it sends another 1500, and then another 1500. So now we're at 6,000 bytes, so it sends back 6,001. So now, why would we not want it to be at 1,500 and send back? Okay, well, every acknowledgement means that it has to pause and wait for data. So if our window size was 6,000, our data would get there a whole lot faster as long as it was getting there than if our window size was 3,000. And so that's why our window size is always changing, is because the more data we can send without an interruption, the better. Okay, so now there's actually a quiz, and it's a great quiz to take on this chapter. And anyways, so we have our window size. So our sequence number 1, we send it again, right? So it receives 1500, and so then we send 1501, right? Because we are sending we're sending 1500 bytes at a time. So we receive those two, and our window size is 3000, so we send back. So we send 3001, and it doesn't get there. So we send 4501, and that one is received. But it knows that this is out of order, so now it sends an acknowledgement that it needs 3001, and now, as you can see, it's dropping the window size to smaller. Now in the real world, these numbers are not this beautiful and even. They're all kinds of numbers, but this is just so you can understand flow control. And make sure you really take this quiz and read this. 7225 is so important for understanding window size and flow control, right? How fast we send it. But remember, that's only in TCP. So, overhead versus reliability, right? So, if we did TCP, think about a conversation, you would have to constantly buffer, because it would be out of sync, because we'd have to have these acknowledgments and all that, so we just send them. And what other processes are UDP? We have DNS, which could be both. We have Simple Network Management Protocol, which is a very widely used protocol to program network devices or monitor network devices. Dynamic Host Configuration Protocol, which I hope you guys all know what that is. DHCP gives us our IP addresses automatically, and pretty soon in our chapters we're going to do IP addressing. You're going to find out why DHCP is so wonderful. RIP, which is a worthless routing protocol. TFTP, which is we can do server configuration backups or flash files into IP cameras or IP devices this way. IP telephony, which Skype or whatever, and online games. So that's our UDP, right? Where all the old other FTP and all that are the other ones. So how are they reassembled? They're not, or they are by the application layer. Okay, so that they just send them. UDP doesn't care, it just gets there. If you think about this, if you have ever been on a voice conversation or any of this, you can tell, because sometimes the picture's out, the voice is off, something like that, right? UDP server processes. Basically, they're just sent back. Feel free to look at these, right? But it's the same. We just inverse ports. It's just we're not going to do a 3-way handshake to form a connection and a 4-way handshake to say goodbye. Applications that use TCP, let's see, we've talked about all these ones: HTTP, FTP, Simple Mail Transfer Protocol, and Telnet. Also SSH, applications that use UDP, we've talked about those. Unidirectional ones, simpler requests, applications that can tolerate some data loss. DHCP, which DHCP is, I think, both actually. DNS, both. Oh, never mind. DHCP isn't. I guess it's just UDP. Huh. SMMP can be both. TFTP is one. VoIP and IPTV or streaming. Alright. Once again, if you want to, you can check it out with Packet Tracer. You can do this little quiz. It'd be great because I know you will be tested on port numbers by someone or something, and there'll probably be port numbers in your CCNA, and there could be port numbers on this test. So make sure they're at least going to ask you what these applications, if they're TCP and UDP. So you might want to do that. But anyways, really look into that windowing. I think it's kind of hard to understand, or anything else. If you have any questions, send me an email or post in the discussions. And hope you have a good day.